Well, thank you very much, and apologies for not being able to be there in person, but I still try to give you a entertaining talk. So this is a joint work with Chrystopher and Nehaniv. I'm from Japan. He's from Canada, and we are doing computational exploration. So I have to say a few words about that. But what I mean is that we do programming for epistemological purposes. So we want to learn something about an object, and that's why we write programs. So it's just as a note on the current affairs, that's why we are not really interested in AI tools for coding, because we want to understand ourselves. And that's one reason why we are interested in declarative languages for describing mathematical objects. Because that's exactly what we want to talk about. It's like, what are the properties of these objects? And that's, of course, our research is a bit of a self-referential because we are studying computation by computational tools. So we are interested in theoretical computer science, automata theory, but algebraically, and that is semigroup theory. And recently we realized that, we have to go to category theory, and we have to do our decomposition algorithms there. So yes, I mentioned semigroupoid, or you can call it semicategory. So what is it? Well, there are several ways to understand that. If you come from category theory, you might say that, it's just a category, except that the identity morphisms are optional. Or if you come from semigroup theory, then you say that, okay, it's a semigroup, but you have restricted multiplication. If you take two elements, it's not guaranteed that you can multiply them together. Or if you are not coming from any of those, then it's like, okay, it's a directed graph, which is closed under composition. So we definitely come from the automata semigroup side. So that's why we write composition a bit differently. We write A, B, C as you would feed it into an automaton instead of the usual category theoretical way. But hopefully it's not too confusing. So sure, I mean, I was like, I need to give a mathematical definition as well. Don't worry, I will give an example as well that will help. But semigroupoid, just like a category, consists of objects, which we might call formal types. Okay, so it's like that's how we introduce types. And of course, this is very abstract. So when I say I'm into types, don't think anything fancy. You can just think about just a peg where you can hang your arrows, because we have arrows, and those also have type depending on their domain and codomain, or source and target. And of course, we are interested in composition. This is the fairly natural. If you have two arrows that they match head to tail, then you can have, and you should have, a third arrow. And I highlighted associativity because that's the property we insist on. So it's like, if you multiply or compose three arrows, that's the order of the composition doesn't really matter. So that will be a key thing. But okay, here is the example, because that's the easiest way to think about it. This is a very finite example. So when you do category theory, sometimes you do some very big categories, infinite. But here we just, okay, very small. You have just two objects, sigma and tau, those are the types. And you have these arrows, which later you might think about as functions between them. And in the middle, we have a composition table, or you might call it multiplication table as well. But you see, it is partial. Okay, so that means that, for example, the arrow D cannot be composed with the arrow A. That's why it's empty there. So that's why it's not a semigroup, because in a semigroup, any two elements, they can be composed. And when we think about it, okay, it's like if you order the semigroupoid elements by their type, then you see that you have these blocks. So it's not just any partial multiplication or composition table, but it's sort of like according to their type. You have these blocks in the composition table. Okay, so if you say that, oh, this is still too abstract, well, then you can have a transformation representation. I'm talking about exactly the same semigroupoid here, but now inside the object, inside the type, I have these two states, 0 and 1, or 0 prime and 1 prime. And those arrows, they correspond to these functions. Okay, so that's a concrete representation. Okay, so this is the these are the objects I wanted to mention. And now it's like, let's talk about the questions. So it's like, obviously, when you have a mathematical object, you ask, what are those? How many do you have? And it's like, I'm especially interested in the finite semigroupoid. So I'm interested in enumerating them. And then once you have many, you are interested, it's like, oh, if you have two, how can you decide whether the two semigroupoids are the same? Okay, the directive graph might be drawn in a different way, and the labels might be different, but it's like, are they isomorphic? So that's an important question. And also, what are the different representations and how can we move between them? So I showed you an abstract representation, which is a partial composition table, and I showed you proper sets for each type or each object, and then we have proper functions between them. So it's questions like, if you give me a composition table, what are the possible minimal, in a sense, transformation representations? Okay, so these are the questions we wanted to explore. And so we had this software, we made this software package called Kigen, which means origin in Japanese, and I totally forgot why I chose this name, and I didn't even know that Kanren is also a Japanese name. But okay, our stack is we use Clojure before, and that's how we learned about the core.logic implementation of miniKanren', and then it's sort of became clear that, wow, that's a good way to study mathematical objects. So it's like, for better or worse, we actually don't look under the hood. So it's like, I have only a rudimentary understanding what's going on in miniKanren and in core.logic. I just want to use it. Yeah, that's one type of approach. Okay, so first we want to have the enumerating the abstract semigroupoid. So how do we represent them? Well, it's just a composition table. It's just a vector of vectors, and then we have composer, and that's like just to show a very simple goal. And then it's like, well, it succeeds. It's like if the table really has A, B, the product of those two. And I have a little demo. So I think if I do this quickly, yes, then I can show you. So here is one. This is actually a semigroup. So it's the famous flip-flop semigroup, which is just capable of storing one bit of information. And now I can ask the usual question. It's like, well, we can go forward. What is 0 composed with 1? And well, that's 1. That's not too surprising. And but, well, relational programming, you can ask things like find all the pairs composing to 1. And but what we are interested in, actually constructing the tables. So we have to do something like that. So what would be all the tables that would have 0 composed with 1 giving 1? And well, of course, this doesn't check any associativity or anything, but that's how we work with Composer. So let me try another quick change. Yes, and so with that, we have to encode the associativity, and we have associativo, and This is for semigroup. So this is fairly straightforward. There is absolutely no problem. We just state that they should compose according to these rules. So we just did it for recreating a previous research. Abstract semigroups have been enumerated before. It's a big, long project up to size 10. So there are a lot of them. But of course, we are interested in semigroupoids, and it gets a bit more complicated. Okay, because we have to deal with the situation where the two elements are not composable, and the logic gets a bit more complicated. But of course, well, yeah, we sorted this one out. This is how it looks like with this keyword, and we just represent, we reify that basically they are not composable. And I have to mention the nil fiasco here, because originally we had the idea that, oh, whenever we have a composition table and we cannot compose, the value just should be nil, because that's the most obvious value. What's the result of composition? Nil. And then I tried to run the engine on that, and it's like, it was not quite working, to say the least. And then I realized that, oh, what's going on inside? And this is the time where I actually had to look under the hood. It's like, oh, the logic variables, when they don't have any assignment, they are nil. So it's like, yeah, that caused a bit of trouble. But okay, after that, it started working, and then it's like, this fancy n is just another the mathematical notation for the non-composability. But here are these this partial table. These are some examples. This is what we learned from then. And the first one, S1, that looks like a proper good semigroupoid, and it's like, if you look at the diagram, you see that, oh yeah, that's like if A composed with B, C, that's true, which is true in the table, then this is a valid semigroupoid. But you see it as you don't have many things in there in the table. So it's like, would any table with just a single entry work? And it's not the case, because S2, that's not, it violates associativity. And you see also from the diagram that it's like, yeah, maybe if A would be just a loop as an idempotent, then it would work, but it's not, because A composed with A is not defined, so it has to be a separate arrow. So this started to be interesting. Then it's like, oh, I see, it's almost empty table, and then it's like there is a semigroup behind it. So it's like, I was a bit surprised, although it's like nothing surprising here. You can have a totally empty table, composition table, and that will give you as many different, I think these are just examples of those, many different semigroupoids. These are all type structures that are compatible with this empty composition table. So nothing is composable. So then it's like, well, okay, we thought about that. If you have a a composition table, then it's like, well, you have to check whether the composition is associative, and you also have to check, it seems, that you have a proper type structure. So it's like the arrows, they work out. So we did this type structure inference, and that what it does is like, well, I try to put it into the comments as well, because, well, I don't have the lead bindings before this, so you have to sort of guess it. But it just checks that the compose arrows should have the domain of the first and the codomain of the second, and then it's like, when not composable, they should be distinct. So it's just literally just checking that. And then it's like we concluded that associativity and consistent typing are distinct properties. So you can have a composition table which is like, it's totally consistent with the typing, but this one fails associativity. So it's not even a semigroup. This would be like a semigroup where you have just a single type, or you have just, well, no type at all, if you would say. Or the other one, which is associative, but you don't have the consistent type structure. So yeah, these are distinct properties, but this is how semigroupoids behave. And well, yeah, just maybe just a little demo one more time. Okay, so go there. So yeah, this is the no composition. This is a totally empty composition table. And if I say it's like, oh, I want to have a type structure inferred for this one, and I want to have just one object. So I'm asking for a semigroup. This is obviously not a semigroup. Yeah, it's empty. And then it's like, if you have two, well, you see, I'm not checking symmetry here. So it's like all the arrows just go uncomposed one direction or the other direction. And just to say that for the flip-flop, we can have the semigroup type structure when you have just a single object. Okay, so back to the slides. So other topics, I mean, we explored a bit more in the paper. I just briefly mentioned them here because we don't want to spend too much time on it. That would be like a longer talk. But then, of course, we were interested in constructing the morphisms. So it is the structure preserving maps from one semigroupoid to the other one. And the key idea was that, okay, we have the composition as a function. So A composed with B is C. So then how to express relations? Well, it's easy. We can just say that A and B are C related. So we have the C relation, all the pairs that compose to C. And the key question is that, oh, what shall we do with the non-composable arrow pairs? And it's like, and you do have a decision there, because if you say that, oh, I want it to be strict, so composable arrows should go to composable arrows and non-composable arrows should go to non-composable arrows. Okay, so that's one way to do it when you consider this and relation as well. So that gives you a stricter morphism. Or you say that, oh, all I care is just to get the composable arrows to composable arrows. And non-composable arrows can go to composable arrows. So that is like, we always want to do this, like mapping everything just to the identity, right? So if we go strict, then we couldn't do that. So yeah, that was the key question there. And then we have this other issue, the arrow type semigroupoids. We called it like this, maybe as like we are waiting for someone coming and telling us like, oh, this has been studied and it has another name. So the idea is that there is always a morphic map. So if you have a semigroupoid structure, you can always have a homomorphism down to the arrow type semigroupoid where you have a single arrow for a function type. So you only have a single arrow between two objects. And I will show you later, as like we computed this full, it's not full, as infinite table, as like a big table, and try to enumerate the these arrow type semigroupoids. And that's also an interesting story. And then, of course, if you remember, I had the abstract representation of the semigroupoid, and we want to go to a transformation representation. Well, of course, because we are coming from automata theory, for us, the transformation representation, that's the state transition. So it's like for a semigroupoid, we expect that, or we want to have basically a finite state automaton, but with restricted modes. Okay, that's the idea of the semigroupoid. And you know, we could do this directly. We didn't do that, but it's just we just reused the isomorphism code. Okay, so it's like, and we did this in a semigroup theory. You have the full transformation semigroup containing all possible transformations of a certain degree, a number of states. And then if you want to have like a four-state representation, can you morphically map your semigroup into that? Okay, and if you can, well, there is a 4-state representation. If you can't, well, then you could try with 5. And then, so we could do this, but what are the full transformation semigroupoids? Because there is only one full transformation semigroup, but for full transformation semigroupoid, you have many, because you can have an underlying arrow type semigroupoid and then put a number of states there. So it's really a multi-dimensional enumeration. So, well, yeah, I mean, we did a few, but that would require a bit more systematic research on that. So let me just show you. It's back to the arrow type semigroupoid. So this is what we got. So these are the number of dots, the number of objects, and these are the number of arrows. Okay, and obviously you cannot have meaningfully a 3-arrow object with only a single arrow, because then it's like we consider that if you have an object which doesn't have an arrow, not even an identity, then okay, we discard that. And also, after a while, if you have 7 arrows, well, you can't really do that with 2 types, 2 objects. You need to have at least 3. So we did this. I mean, in the paper you see at the bottom as well. These numbers are not on the online encyclopedia of integer sequences. So that means that it's like, oh, maybe no one calculated this before, and maybe that's the reason why there is we couldn't find any name for this arrow type semigroupoids, but we will see. So it's just a bit of reflection on using the core.logic. I would say that the maybe just mine, but the learning curve is a bit steep because documentation is a bit scattered. And yes, I do have the recent schema and all the other books of that type. But it's like when you already want to solve something, it's like, oh, do I have time to sit down and read those books? Because obviously the answer is there. So that's a bit difficult. And I'm happy to see that there is work going in the direction of working with sets, but that would be also quite useful. But what we would like to have is that working with hash maps, because that's what at least I do in Clojure all the time. So when we go relational, we need to convert the algorithms to the list-based operations. And also, it's like when we did the enumeration for the semigroups, you want to exclude all the 3 nilpotent ones. Most of them are non-interesting. You have 3 elements, you multiply them, you get a 0. So it's like, would be interesting how to express this thing, excluding the 3 nilpotency. But okay, I think my time is up. So let me just end here. Thank you.
I presume we have 1 minute for questions. So perhaps one question can be asked. No? Yeah.
I guess just out of curiosity, you showed this big table of numbers you generated for how many of these semigroupoids there are. How much time did that take?
Well, at the very end, I started running the search like 2 weeks ago, and hoping that it's like, 2 weeks time. So there are several tricks. We can be clever. We can do that, but it's like 2 weeks time. There was nothing. And I don't know. The isomorphism checking takes a lot of time, because you want to check that up to isomorphism how many you have, and then it's like if you have a big isomorphism class already, you have to check all of them, and then it's like all of them would do the full run. So yeah, this graph isomorphism, it's like it's difficult to calculate.
Thank you.
Thank you. Let's thank the presenters once more.